Optimization. So, look, there's not a whole bunch of like straightforward steps to solving optimization problems. These come from our text, and I think they're good. You're not necessarily doing them in this order. And I don't want to make you memorize them. You're not going to be tested on, hey, what are the steps to solving optimizations? This is just kind of a good guide how to get started. So number one, I always feel like is a little bit condescending. Understand the problem. But really what they mean is like especially with word problems that can be intimidating, there can be sort of a panic students where you just want to dive right in and start doing calculations as you're reading, and that's generally not the best way to do it. I would say go through. Optimization literally means either find a maximum or a minimum. So maximize or minimize. Read all the way through and make that decision first. What is it that I'm trying to maximize? Am I trying to maximize area? Am I trying to minimize cost? And then you're going to develop a notation. In some problems, it's going to be really helpful for you to draw a diagram and then kind of label. So you're doing kind of steps 2 and 3 simultaneously, where you'll be like labeling and drawing, labeling with a notation and drawing at the same time. So which is why I said this isn't necessarily like a step-by-step linear order. And I took some of the function names because you're not always gonna name the functions the same thing. And then 4 is just such a weird step. It says express your function in terms of the other symbols from step 3. So this will make more sense once we do a problem. I'm not even going to try and explain it, but it's like you'll have, your area of a circle is pi r squared, but you're given your radius as some other function of time. So then you're going to do a substitution of the r into whatever they told you the function of time was, right? So you're basically like making a substitution at that point. All right, so if your function has been expressed as a function of more than one variable, then you need to use the given information to find relationships and eliminate all but one of the variables. So your goal, we know how to find the maximum of a function. We know how to find the minimum of a function. We just did it in the warm-up, right? You take the derivative, you find the critical values, figure out where the function increases or decreases, then we can find the maximum or the minimum. But before we can do that, we need our function in terms of a single variable. Once we have that, we're good to go. Now we're just doing calculus. And then we'll use the sections that we just went over to find the absolute maximum or minimum if the domain is a closed interval. And so that's it. I can really summarize that as read the problem, draw a diagram, build your function using notation, get it in terms of one variable, find the maximum or the minimum. All right, so let's try. We're going to try a couple, and then I think I put one of the problems from the AP exam in 2017 at the end. All right, we're going to do this video game style. I'm a Nintendo man myself. I like the Mario-averse. We're going to do this just like Mario would, where start off stepping on a Goomba, move up to a mini boss, then we get to Bowser by the end of this. Okay? You guys know, does that analogy track? All right, so a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So this one, the order probably makes the most sense. Let's diagram it so we know what's going on here. We got this straight river. And we're going to make a rectangular fence, but it doesn't have to have a side along the river. No, that's not a picture of an idyllic farm that I took and pasted in here. I actually drew that by hand. All right, so we have a rectangle here. What is it we're trying to optimize? What are we trying to find the maximum or the minimum of? Area. I'm going to just make a note of that. I want to specifically, I want to maximize area, right? So then here, let's come up with some notations. We want to label the sides of our rectangle. What do you want to call this side? You guys are going to freeze up on naming it? Think, what's your favorite letter? No, that already means something in math, Maisie. Okay, what if we do height, H? Is everybody okay with that? Does that offend anybody's sensibilities? We can do math without X and Y if we feel like it, right? What are we calling this then? Yeah, I'm going W. Who said T? Chase, take a timeout. Come on. W. Okay. Now, what's the 2400 reference? Okay, actually, before we do 2400, we're trying to maximize area. In terms of what I just defined this as, what's the area of that rectangle? In terms of the labels we just gave it, what's WH or HW, right? Good. So that's the function we want to maximize, but before we can do that, we need to get it in terms of a single variable, correct? All right, so then we're given some information, which is this 2,400 feet. What does that 2,400 feet refer to? What about that rectangle does it refer to? The perimeter. Still the perimeter, right? It's just not the perimeter of a full rectangle. But what's the perimeter of this rectangle? What would the formula be for the perimeter of this rectangle? 2h plus w. Now we're going to assume we're going to want to use all the fencing, right? So I'm going to say that has to equal 2,400, doesn't it? And so now I have this other piece of information that will allow us to put the area function, which is the thing we're trying to maximize, in terms of one variable, right? Now, which variable do you want it to be in terms of, h or w? Does it matter, really? It doesn't matter, so whichever one's easiest to isolate, usually. And I agree. Did you say w, Maisie? So if we do w equals 2,400 minus 2h, and sorry, this is going to put it in terms of h. We're isolating w. Because now what we'll do is go back and substitute. Take that 2,400 minus 2h. I'll plug it in for w there. And I'll get a new area function that's strictly in terms of h. So a equals h times 2,400 minus 2h, right? So that's the function I want to find the maximum of. First thing I would do is probably just distribute the h. (2400 minus 2h squared). Okay. Then I kind of want to think about what's the domain of H. Oh, thank you. What's the domain of H? What's the biggest H could possibly be? If we're going to have a rectangle. And 1200. So H has to be less than or equal to 1200, right? Because if H is 1200, then it's 1200 on, then this side is 1200 and this side is 1200. And we technically are, what's our width then? 0. So it's not a real life rectangle, but it is a mathematical rectangle. We call it a degenerate rectangle. So it still works mathematically. It just doesn't make sense. Like, would he want to build that? Could you keep horses in that field? No. But that's still our upper limit for H. What's our lower limit for H? 0, the other extreme, right? So H has to be between 1200 and 0. Now, we know that absolute maximums and minimums can occur either at critical values or at the endpoints, right? Is either of these endpoints going to maximize the area? What's the area going to be at both of these endpoints? 0, because both of them are going to give us a degenerate rectangle, right? Which has no area, because the sides fall right on top of each other. All right. So the maximum is going to occur at a critical value. So let's find the critical value. Let's take the derivative. So A prime is just going to be what? 2400 minus 4h. Critical value, set it equal to 0, right? Okay, so 2400 minus 4h equals 0. I can divide out 4 from both sides. I'll get 600 minus h is 0. H is 600. All right, so there's only one critical value, so let's cross our fingers that this is the value that will give us the maximum area, right? If it's not, we're in trouble, because we already found out that the endpoints give us 0. So this is something where, Maisie, you couldn't use that technique you were talking about. That technique you were talking about is great for multiple choice questions, but on free response, the College Board is very specific about how you justify that you know it's a maximum or a minimum, okay? So I'm going to go through that now. Do the same thing we've been doing, which is put it on a number line. That's 600. We're talking about A prime. We know that A prime is 0 at 600. So it has to be either positive or negative everywhere else. And so we'll just check in other places. If I plug in, let's say 0 for A prime, do I get back a positive or a negative? If I plug in 0, I get back positive. That would just give me 2400. So what is my original function doing on that interval? It's increasing. That's a good sign for us. Plug in something from over here, maybe 800. So then you would have 2400 minus 3200. That comes back negative. So my original function is decreasing, right? So at 600, A goes from increasing to decreasing, which means that 600 is the location of a local max, correct? Now here's the thing. There's a big paper on the College Board website where they detail why this isn't sufficient work to prove that there's a local maximum. And the thing is that what we just verbalized, you need to write out. So you can't just use the number line diagram if this is a free response question. You have to write out basically a concluding statement showing you know why there's a local max at 600. So it can be as easy as this. I'm going to use the backwards E. You guys remember what that means? You weren't studying math notation over spring break? Not cool. Backwards E just means there exists. So I'm just going to say there exists local max at h equals 600 since a prime is greater than 0 when h is less than 600 and a prime is less than 0 when h is greater than 600. So all I'm doing is I'm writing out, and you don't have to use the shorthand notation that I use. You can verbally write it out if you wish. But I really want to point out that you need this. You will not get full credit if all you do is give the number line diagram. Okay, that's your justification for knowing that there exists a local max. Everybody with me? Zoom, you with me? Okay. All right, now let's answer their question, which is, they specifically asked, what are the dimensions? So I know that h is one of the dimensions, but I need to know the other dimension. I'm going to say the dimensions are 600, what are we in, feet? Yeah. By, so if h is 600, what does w have to be? 1200. You can kind of just intuit that, or you can look to this. We have this equation relating w to h. So you can just plug in 600 for h and solve for w, right? We get 1200. They don't actually ask for the maximum area, which would be those two multiplied out. They just ask for the dimension, so I'm going to stop there. So there's our first optimization problem. All right, let's do a couple more. All right, this is a really minimal one. That's always math, specifically like the AP exam in math, can be tricky like this, where the more verbose a problem is, usually the easier it is, and the more concise it is, the harder it is. All right, so a cylindrical can is made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. All right, let me ask a couple questions. What sort of optimization are we trying to do here? We're trying to find a maximum or a minimum? What are we trying to minimize? The cost, but are we given any information about the cost? No, but what would the cost of metal correspond to? Surface area. Perfect. So this one's a little tricky, right? It seems like you want to minimize cost. They don't tell us information about cost, but cost is going to be directly proportional to surface area because that's how much metal to manufacture the can. So that's what we want to do. We want to minimize surface area. I'm going to call surface area S. Great. So let's draw a cylinder. Okay. Well, all I know is that it has to hold 1 liter of oil. So here's some things you know about a can. You have a radius, you have a height, right? All right, so let's come up with the general formula for surface area. Well, we got the top and the bottom, and those are circles. So what's the area of a circle? Pi r squared, and there's 2 of them, right? All right, so S equals 2 pi r squared. And then you got your lateral area. That's your koozie coverage. It's where you put your koozie so your hand doesn't warm up your beverage. This space here, right? All right, well, I like to think of that as just, it's actually a rectangle, because if you cut down vertically on your cylinder, and then you laid it flat, it'd just be a rectangle, right? Its height would be h, but what would its width be? So if I cut that vertically, close, you're getting there. Circumference, which is what? What did you say, pi d? Oh, it's pi d, or 2 pi r, right? This corresponds to this, if you cut it and lay it flat. So this is 2 pi r. This is h. And then the area of that rectangle is just 2 pi r h, right? Thank you, Vincent. So that's great. That's what I want to optimize. But how many variables is it in terms of right now? How many variables do I need it to be in terms of? 1, and then I can do calculus with it, right? All right, well, we have this other piece of information, which is that it needs to hold a liter of oil. What is a liter referring to? Volume. So this is referring to volume. So volume of that, the volume of any type of a cylinder is the area of the base times the height. What's the area of the base in this case? Pi r squared. It's the circle. So pi r squared times the height. Here's the other thing this one is getting tricky with. They tell us that volume has to be 1 liter, right? A liter isn't a unit of volume that's going to convert nicely into units of surface area. Like there's no corresponding surface area dimension to a liter. But you guys aren't from Europe, so I don't know how familiar are you with the metric system. What's 1 liter in cubic centimeters, if you had to guess? No, so you're thinking like Americans. You're like, there's like 16.5 ounces in a cup. You're getting better. I have to check just to make sure. But I'm pretty sure it's, yeah, I think it's 1,000. Yeah, it's 1,000 cubic centimeters. That's what's nice about the metric system. It's always multiples of 10. So 1 liter is 1,000 cubic centimeters. Then we're working in cubic centimeters, which will be much easier to transfer to surface area, because then we'll have square centimeters for surface area, right? So I'm just going to convert that 1 liter to 1,000 cubic centimeters. All right, so I have pi r squared h equals 1,000. So now I'm at the point, I have these 2 equations. I would like to get my surface area equation just to be in terms of a single variable. And now I think we're prepared to do that, because we can use this equation to do so, right? In that volume equation, what's going to be the easiest to isolate? Is it easier to isolate H or R? Probably H. I don't want to do a whole bunch of taking the square root of stuff. So what we're going to do is isolate H, and we're not going to touch our calculators until the end. We're going to keep things exact. Meaning, when I isolate H, that's what? 1,000 over pi r squared, right? I'm going to leave it just like that. All right, now let's go ahead and take this, and we'll plug it in for H in our surface area equation. So we'll get S equals 2 pi r squared plus 2 pi r, and instead of H, we're replacing it with 1,000 over pi r squared. All right, before we do calculus with this, we're going to simplify as much as we can. So notice that this pi in the denominator will cancel with this pi in the numerator. I have r over r squared, which can be simplified to r to the negative 1. And 2 times 1,000, so I have 2,000 r to the negative 1. Right? Did I leave anybody behind there? Are we good? Okay. Good, so this is just my surface area of a cylinder equation, but only as a function of its radius. And now I'm ready to do calculus. I want to minimize this, so I want to find the absolute minimum. Let's take the derivative, same thing that we've been doing. Derivative of 2 pi r squared, if r is our variable, is going to be 4 pi r. Now, derivative of 2,000 r to the negative 1, you're going to have to bring down the negative 1, so it's going to be minus 2,000 r to the negative 2. So another way of writing this is it's 4 pi r minus 2,000 over r squared equals 0. Now I want to point out a technical math thing again here. Critical values are where the derivative is equal to 0, or there was another time that they would be considered a critical value. The derivative equals 0 or what? This one doesn't come up that often. Let me give you an example. Like if you're looking at a function like this, that would end up being critical value. What's going on with the derivative there? It's undefined. Oh, Olivia on Zoom bailing you guys out. Undefined, yes. Right. So if the derivative is 0 or undefined, that's considered a critical value, right? Now, are there any values of r that would make this undefined? 0. Now, r equals 0 is technically a critical value because it would make this undefined. But now when we jump back from math world into real world, are we going to be making a can that has radius 0? No. That exists in math land. In the real world, what volume would that have? 0. It's a degenerate cylinder, right? So it's still important for me to point that out because there can be cases where you'll have a critical value where your function, your derivative is undefined and it is a maximum or a minimum. It's just not the case here. But we did acknowledge that r equals 0 is technically a critical value. Now to solve this, what we'll want to do is just multiply through by r squared so that we're making this a situation where we don't have a fraction anymore, right? So if I distribute r squared, I get 4 pi r cubed minus 2,000 equals 0. All right, then we're going to solve for r, but we're going to keep it exact. So take this kind of step by step. 4 pi r cubed equals 2,000. R cubed equals 2,000 over 4 pi. Now that'll actually reduce a little bit. 2,000 divided by 4 is just 500 over pi. And then I'll just take the cube root. So r is the cube root of 500 over pi. All right. And so now this is a critical value. We need to verify that it's actually the location of the absolute minimum, right? So number line. We're going to test this in specifically S prime. This is one where it's much easier to use your calculator probably, because S prime isn't like a nice function down here. It's not easy to just do in our head and plug in values, so I'm going to utilize my calculator for this one. But here's what we do know. We do know that S prime is 0 at that weird critical value, which I don't know what that is off the top of my head. We need to choose a number to the left and to the right of it. So calculator, let's do that. I'm going to go to y equals, I'm going to put my S prime function into y1, and S prime was 4 pi x minus 2,000 x to the negative 2. All right. So first, let's go to our table. Do you guys know how to find the cube root in your calculator? It's in math. It's the fourth option down. So I do the cube root of 500 over pi. I already know that that should be 0, right? And it is. But honestly, I had no idea what the cube root of 500 over pi was approximately, which is why I did it there. It's about 5.4193. So first thing, let's choose a number to the left of that. What's a number to the left of that? 0. That's a problem, though, because that's technically a critical value, so it's going to come back undefined, which is not what I want, right? And I'm also going to make my radius bigger than 0. So what's a number to the left of that, but not 0? 1, 2, any of those will work. All I care about is the sign of the derivative here. So the derivative is negative, right? All right, the derivative is negative, so my original function must be decreasing, yeah? So negative, my original function is decreasing. All right, let's choose a number to the right of that. What's a number to the right of that? 6? Yeah. And the derivative is positive there. So my original function is doing what? Increasing. Positive derivative, meaning original function must be increasing. Okay, which means what's going on at the cube root of 500 over pi? That's a minimum. And look, this has to be also the absolute minimum, namely because this is quadratic, and if it's a minimum on the quadratic, it's the absolute minimum. It's the bottom of the parabola, right? But just like before, the critical values of the endpoints, the smallest the radius could be is 0. That produces a degenerate, cylinder, meaning a cylinder that technically has a volume of 0. And the biggest the radius could be, it's unlimited. It could technically, we could continue to get the radius to be infinitely large, but that would also create a degenerate situation because as the radius get bigger, the height would have to shrink to 0. Does that make sense? So this has to be the absolute minimum. All right, so let's make our final statement here. Let's make our conclusion. So there exists a minimum at r equals the cube root of 500 over pi, since the derivative goes from, so since s prime is positive, no, is negative, sorry, when r is less than that critical value, and s prime is positive when r is greater than that critical value. All right, and the last thing we have to do, now we've proven that that's the location of our minimum, we have to answer their questions. Find the dimensions that will minimize the cost of metal to manufacture the can. So the dimensions for us are R and H. And we know R, and it's at this point that I'm going to approximate R, because if I'm working at the can manufacturing plant and I'm your manager and I say, Kai, go out there and find me the dimensions that will minimize the cost to make this can, and Kai comes back and says, well, we just need to do radius cube root of 500 over pi, I fire you on the spot. That is not good context for keeping things exact. So we want our radius, we want our dimensions to be, and if you're going to approximate in calculus, it's at least 3 decimal places. So my radius is approximately, hold on, let me go back to my calculator. What was it? 5.419. And we would be in centimeters. By my height, that's going to be approximately, and I can find that, just my height is 1,000, so over here. My height is 1,000 divided by pi times my radius squared. So I'm going to go back to my calculator and go, oh boy, you got to be really careful with this one. So 1,000, starting off strong, divided by open parentheses, pi, times my radius, I'm going to open parentheses, is the cube root of 500 oh no, wait, that needs to be under that. Shoot. Wait. There we go. Divided by pi And I'm done there. Close that, and then it's the radius squared, so I have to square that. And then close out my, there we go. I think that's it. 1,000 divided by pi r squared, that'll do her. So the height is approximately 10.839. Whoops. I wrote that, so 10.839. Okay, folks.